Hello everyone, welcome! In this video, we are going to take a look at a slightly more elaborate audio visualization example. This is the updated version of a previous example which we showed how you can do audio signal visualization with Copernicus. In this case, we use the CHOP network to drive a parameter here inside the Copernicus network, in this case the equalizer load. And then we can see how the result directly maps to the final image. In this case, we are going to look at a slightly more complicated setup, which involves a complete scene, and we are going to render it using Karma. So let's take a look at the result. Here, I already have the setup. Alright, so that is a setup, and I'm going to walk through all the setup. So here we have the geometry, and we create the ground plane. And for the purpose of audio itself, we have the audio panel scrub and set the output to the audio signal itself. We're going to take a look at this network later. For the geometry, we are just using some box, a very simple box, and we are just manipulating the center of the box to put it centered at the lower button, so the box sits on top of the plane. Actually, I wanted to do a bevel, but I only realized that after I have set up everything. Otherwise, I would also put a poly bevel somewhere below this one, and maybe use a transform instead of directly manipulating those ones. That way, the render result looks a little bit better. But anyway, for the purpose of this setup, I am driving the size by the audio signal. So this is pretty much the same setup as the previous image generation example, but here I'm going to show you some details of how we can specifically set up those different bands. The original plan here, as you can see from the name of the geometry, I was trying to divide the entire vocal range into 10 buckets. So just as a reminder, if we take a look at something like 40K audio frequency range, it will show you that even though the sampling rate is 48K, the actual audible signal is up to 24K, and the human hearing range is from 20 Hz to 20K, right? So here what I'm trying to do is just to divide those into 10 buckets, and then use each bucket, represent each bucket as a box, and then when the music's playing, just varying the size of the box. So pretty straightforward setup, which didn't really work, but we'll take a look at why. So here we see how this set up the position and the sizing, so that part is very straightforward. If we now go to the channel network, here we have a motion FX or channel network. As you can see here, we read the file, and that is direct audio output. And then let me take a look at the result below. So that's a previous setup. So previous setup, I'm using a band pass filter and just divide everything into 10 equal baskets. And you can see we have 2000, 4000, 6000, and then generate an envelope directly from there. Let's take a look at the result. So here, if we take a look at the file and disable the other one, and then you can see we have the band pass filter, and then we just do an envelope, and then we delete the one channel of the envelope because the envelope outputs 2 channels, right? I don't know what the second channel is for, but the first channel looks like the actual envelope, and then we just export it to the corresponding geometry and drive the size Y properly. So this one didn't really work, and the reason for that is if we take a look at the spectrum, and you can see if we go to somewhere here, and notice we are looking at the samples because all the sample index is divided by a specific number. Okay, the number is not shown here, but previously I have captured the number 0.01. So I did a stretch of the entire sample index, and then everything is drawn in this range. As you can see, the majority of the signals are centered around this area, right? So from 0 frequency to 4000. So if we do as I previously planned, the majority of the frequency don't have any data. So when we drive the result, using this network, the end result is that only the first bin is changing size. The rest are remain like the ground level. So that's why I changed my strategy, because most of the information is around this one. So a log scale is thus preferred that focuses or compresses all the data to 0 to 4000 Hertz. And to do that, I've picked a multiplier of 2.5 is chosen as multiplier. So what do I mean by that? So if we look at the bandpass now, it's from 0 to 10, 10 to 25, 25 to 63, 63 to 158, and so on and so on, right? And each number is 2.5 times the previous number. So in general, if we go through all of those bands, we still reach, oops, wrong button. We still reach the last bit, which is 20K, but now we have better information concentrated in the earlier bands, right? The rest of setup is very straightforward. So we get the audio signal, we do a band pass filter. So if we take a look at this here, and then go to here, do a band pass filter, do an envelope, and delete one of it, you see those signal. On the other hand, if we, I think there's a way to just look at one of the things, but I have to toggle everyone off. So here, each one shows somewhat different, and gradually there's less signal. Eventually, we don't even have much signal going on, right? So that is how it's set up. Now, after everything's done, make sure you export everything so that inside the object network, we are driving everything properly. If we go back to 3D view, because this is a very small number, it's a range from 0 to 0.5 or something, I have applied a global scale. Otherwise, the size change is not perceptible. So I applied a global scale to make it more obvious. So that's the setup for the geometry side and the channel side. Now, if we go to stage, this is where we set up the rendering. For the rendering, we are using two SOP import to import the ground object and the viz object, which is the actual visualization, and then point them at this path. So if we take a look at the scene hierarchy, after the second step, we have the scene, kind of like a folder, and then we have two objects. And then we add a transform. Now, this step is because you will be surprised if you just import the viz, the scale is not imported. So previously, when I set up this guy, we set a scale here, right? But as it turns out, when you are importing those geometries in the SOAP context, the scale is not transferred. So I have to do another transform specifically on this viz primitive and then set the scale to 100. That way we can actually see something. And then now if you play with this, oops, what's going on? Oh yeah, we haven't set up lighting yet. And then we add a camera physical sky, and then add a camera. And if we go to the camera look at this angle. And then we add some material. So for the material, I'm just using a very simple, where's my material? For the material, I'm using a very simple, yeah, it's not shown here, but this one is actually a quick surface material. Which will become a edit material properties. A quick surface material to create a material called glass. And actually, I try to make a fancier glass, but I'm not able to do that. So, doesn't really matter. And then I assign the glass material to the viz object, and then do some comma render settings. And then finally, if we take a look at here, it's a bit slow, but you see everything going on here. Now in the comma render settings, some of the things I changed. I am disable the depth of field and motion blur, and for the image, I'm using Intel oiling as the filter. For some reason, NVIDIA optics doesn't really work on my machine. I don't know why. And I use this one so that I can make the samples very low. Instead of spending a lot of samples, I'm just make it very cheap. I don't want to spend too much time doing the final rendering. The important part is how these bins are set up. And then I'm just going to do a final render into the folder using the specific render settings. Make sure I'm using the comma XPU and then render to disk. Now there's something I don't fully understand here, which is it appears that when I'm actually doing the rendering, so I'm just going to click render to disk again, although I already have the results. So just to show you, the final results is rendered inside the quick render, which contains all the denoised version of the images, and then I'm just using Blender to combine everything into a final result, which I'm going to show at the end of the video. So something I don't quite understand is when I render to disk, right? So it starts rendering, and if you take a look at the performance, and I'm a little bit surprised to see the rendering process seems to be CPU bound. So in this case, I see CPU is 100%, GPU is like barely used. I don't know whether there's something I didn't figure out, but I do find this pattern very strange. Even if we interrupt this one, even if we change the samples to 128, which is the default, and then I do render again, right? So supposedly it spends more time in the GPU side, but reality is, you know, GPU is still not really utilized. I don't know what is wrong. So that one is very weird to me. Yeah, that one is very weird to me. And for the camera, if we just move around here, let me just interrupt this. If we move around here, you can see I think optics is not really working. You know what? That might be the reason. Yeah, optics is not really working. So it's just using Embree CPU rendering. Yeah, probably that's the reason. Anyway, so that's the render side of things. And here's the final result. Alright, thank you for watching.